System is on. Beginning ignition in 5, 4, 3, 2, 1. This is a thrust stand. This is used to measure the amount of force produced by an engine or a motor or whatever you want. However, we need something larger for our Starship. This is a custom frame for our new thrust stand. In today's video, we'll be finishing this build and testing some engines. Hello Internet, welcome back. It's been a while. Sorry for the delay. Let me catch you up on what we've been working on. We are building a rocket. Not any rocket, but a functional vertical takeoff and landing rocket based by SpaceX Starship. There are 4 major components to any full-scale rocket: the structural system, the guidance system, the ground control system, and the propulsion system. In this video, we will be starting development on the propulsion system. The function of the propulsion system is to produce thrust. Thrust is the force that moves rockets through space. There are 2 main categories of rocket engines: liquid rockets and solid rockets. SpaceX uses liquid propellants in their rocket engines. We, however, will be using solid rocket motors. Solid rocket motors will be safer and cheaper for us to handle, but it will also bring 2 major challenges for us to address. First is the ability to shut off and restart an engine. The second is the inability to throttle our thrust. We can solve the inability to restart our engines simply by having multiple engines, one set to fire on the way up and another set to fire on the way down. The inability to throttle the engines will be more challenging for us to solve. There are a few different methods we can try in order to achieve some level of throttle control on our solid rocket engines. First, using thrust vectoring. Second, using the Krusnik effect. Third, using thrust termination ports. We'll talk more about these later. Most importantly, we are going to determine which method of throttling would be best for our rocket. We need to collect some data, and the best way to do that is using a thrust stand. A thrust stand is a device used by aerospace engineers to statically test rocket motors. It is possible to buy these off the shelf, but what's the fun in that? We instead are going to design, manufacture, and build our own. So let's get to work. The first step I do when designing something is to identify the scope of the project. What do I want to make, and what do I need to do? So in this case, what do I want to make? A thrust stand. What do I need to do? Well, there's 3 main things. First, I needed to be able to ignite a rocket motor. Second, we need a way to measure the thrust. Lastly, we need a way to interact with the thrust stand. After we come up with the scope of the project, then we want to do some research to identify what type of devices do we need and if these devices will be able to work together. Next, it's time to design the hardware. Jumping into Fusion 360, this is where I designed the thrust stand. The thrust stand frame is made out of aluminum extrusion. The electrical panel is located between the legs, and they're used to house all the key electronics. For each component I design, I think about how strong should these components be, what material should they be made out of, and how should they be manufactured. After planning out all of that, it's now time to start manufacturing.
Eventually.
After weeks of work, the thrust stand is done. Now it's time to start firing some rockets. We will begin our test by seeing how well thrust vectoring can be used to throttle our rocket engines. By firing our rocket motor in line of the vehicle, this should produce the largest thrust available. Fire in 5, 4, 3, 2, 1. Second, we'll tilt each motor 30 degrees from center to measure the change of thrust. We can predict how much thrust we will expect to see at this angle by doing some math. But let's confirm this by running the test. Beginning ignition in 5, 4, stay in your 3, 2, 1. After completing our test, we measured a 15% drop of thrust from our control fire. At 30 degrees, we measured 8.06 newtons compared to original 9.5, which is very close to what we expected from our mathematical model. It's time to test the Khrushchev effect. The Khrushchev effect is a phenomenon when a rocket motor is significantly recessed inside a vehicle. The exhaust gases expand below atmospheric pressure. Once the exhaust gases are below atmospheric pressure, they will no longer produce significant thrust. We will test this effect by using a sliding cover. We'll use this cover to recess the rocket into different distances and measures the difference of thrust generated at each distance. 4, 3, 2, 1. 3, 2, 1. 5, 4, 3, 2, 1. Firing. After conducting a series of tests, the results of the Khrushchev effect was mixed. The first 3 tests did not have any significant influence on the thrust output. At 9mm recessed, we had an increase in thrust by 1%. At 11.15mm, we had a reduction of net thrust by 3%. And at 20.75mm, we had a reduction by 4% from our control starting point. It wasn't until we passed 37.2mm, nearly 1.5 inches, did we see a significant effect. At 37mm, we saw a reduction of 21%. Let's summarize our findings and how they would relate to SpaceX Starship. SpaceX can throttle down their engines down to 40%. But using our current methods, the max we are able to reduce is 21% by using the Khrushchev effect. The problem with using the Khrushchev effect is while you are lowering your thrust output, you will also lose the ability to use thrust vector control. You will also experience structural damage if you attempt to go too far into the rocket's body. So we determined not to use this method for our rocket. The thrust vector control test that we conducted was at 30 degrees. And we saw a 15% reduction in thrust, but this is very optimistic. SpaceX Starship and Falcon 9 only has a max thrust vector control tilt of 15 degrees, half of what we tested. And it's very likely that we will need to make compromises on how much throttling you'll see solely from our thrust vector control gimbal. There is a third method of throttling that the rocket engines could use, which is the thrust termination port. This port terminates the net thrust by reversing the direction of the exhaust gases. This method could also be set up to generate reverse thrust. However, we'll be saving this for a future video. So make sure you're subscribed to the channel to follow us. The data we collected was very useful. It highlighted methods that didn't work as well as we might have hoped. With our new insight, we could better design our first test vehicle. Next, we're beginning our testing on our custom thrust vector control hardware and our unique landing system. So if you want to keep up with this project, make sure you click that subscribe button down below. See you next time.